Hey everybody, today we're going to do some harder problems finding areas between curves. Here's the 3 problems we're going to do. Let's jump right into it. Problem 1. Find the area enclosed by y equals secant squared x and y equals 2 between x equals 0 and x equals pi over 3. So things are going to be a little harder because we have trig, but there's a bigger issue than that here. If we look at the picture, we can see that the graphs intersect in between x equals 0 and x equals pi over 3. So there isn't just going to be one top curve over the entire interval. Remember, our basic idea for finding areas is to integrate top curve minus bottom curve. So our strategy is going to be to find out where these graphs intersect and then write 2 different integrals, one for the left shaded region, one for the right shaded region. So we set y equals secant squared equal to y equals 2. Remember that secant is 1 over cosine, so we take the reciprocals and the square roots of both sides. Recognizing that we only care about the answer to this equation between 0 and pi over 3, we get that x is pi over 4, because the cosine of pi over 4 is root 2 over 2, or 1 over the square root of 2. So, to summarize, between 0 and pi over 4, y equals 2 is the top function, and between pi over 4 and pi over 2, y equals secant squared is the top function. So we can write that shaded area as 2 integrals. From 0 to pi over 4, top minus bottom, 2 minus secant squared x. And from pi over 4 to pi over 3, top minus bottom, secant squared x minus 2. Now we just need to integrate. We find antiderivatives. There we go. Remember that the derivative of tangent x is secant squared x. So the antiderivative, n antiderivative of secant squared x is tangent x. Next, we have to plug in. The big bracket on the right is going to be plugging into tangent x minus 2x. The smaller parentheses there on the left are plugging in the pi over 4 and 0. Remember that 2x minus tangent of x at 0 will be 0. A little bit of simplification, and we get pi over 3 minus 2 plus the square root of 3, about 0.78. Problem 2. Find the area enclosed by x equals y cubed minus 7y squared plus 12y plus 1, and x equals negative 2y plus 9. So right away we're suspecting we're going to want to use horizontal rectangles. We see that x is solved as a function of y. And when we draw the pictures here, that only confirms our suspicion. In particular, if you look at that uppermost shaded region there on the left, both the top curve and the bottom curve are going to be defined by the x equals y cubed minus 7y squared blah 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 equation. So horizontal rectangles are going to be a lot easier here. Even then, however, we see that we're going to have to break this integral up into 2 pieces. In that uppermost region, the right curve is going to be x equals negative 2y plus 9, and in the lower region, the right curve is going to be the cubic. So we want to find out where these graphs intersect. It sure looks like they intersect at 1, 2, and 4, but we can't just assume that those values are exact. And then once we have those intersections, we can actually set up some integrals. So let's do it. Let's take these 2 polynomials and set them equal to each other. When we have 2 equal polynomials, we want to put everything on one side, so we get something equal to 0, and then factor. So I used a bit of a shortcut here. I knew that it looked like the graphs intersected at 1, 2, and 4, so I suspected that the factorized form was going to be y minus 1 times y minus 2 times y minus 4. So I just foiled that out to check my work, and it ends up that I got the right answer. Fantastic. So to summarize conclusions from that graph and from the algebra up above, the 2 intervals we're interested in are 1 to 2 and 2 to 4. On 1 to 2, the cubic is the rightmost function, and on 2 to 4, it's the straight line. Let's actually set up some integrals. So from 1 to 2, right curve minus left curve, the cubic minus the straight line. And then from 2 to 4, right curve minus left curve is going to be the straight line minus the cubic. We simplify, combine some like terms, and then we're ready to integrate. It's not a coincidence that the 2 integrands are identical. We are taking the same 2 functions, we are just subtracting in opposite orders. That's like multiplying by negative 1. That's going to save us a little work as we anti-differentiate. So let's actually do it. In each term, we raise the power by 1. divide by the new power. Then we're going to plug in from 1 to 2 and from 2 to 4. Do a little bit of arithmetic. Overall, we get 37/12, approximately 3.08. Problem 3. Find the area of the triangle with vertices 2, 1, 4, 3, and 1, 4. So there's many ways to do this area problem, including linear algebra. We're going to do this the calculus way. Here's the picture. Looking at it right away, we can see that not only is there not a consistent top curve and bottom curve on this graph, there's not a consistent left curve and right curve on this graph. So we're going to need to write two integrals, whether we do this with vertical rectangles or horizontal rectangles. So let's do it with vertical ones. Let's break this region up into two pieces, A1 and A2. On each of these two, we have a single top curve and a single bottom curve. Great. The next thing is that we actually have to have equations for those curves. Now, we know how to find the equation of a line that passes through 2 points. We find the slope, and we use point-slope form. So for that top line, for example, we see a slope of -1/3, a rise of -1, and a run of 3. And we see that it passes through the point 1, 4. So using point-slope form, y minus 4 equals -1/3 times x minus 1. Simplifying that a little bit, y equals -1/3 x plus 13/3. We can get the equations for the other two lines in exactly the same way. That left curve is y equals -3x plus 7, and the curve on the right is y equals x minus 1. So, two integrals for a1 and a2 respectively. For a1, we're integrating from x equals 1 to x equals 2. The top curve is y equals -1/3 x plus 13/3, and the bottom curve is y equals -3x plus 7. From 2 to 4, the top curve is the same, but the bottom curve now is x minus 1. So we've got the problem all set up. Now we are going to want to combine some like terms to simplify those integrals a little bit. There we go. Anti-differentiate. In each case, again, raise the power by 1, multiply by the reciprocal of the power, and then carefully plug in our endpoints. There's some pretty brutal arithmetic here, but nothing we can't handle. Overall, 4/3 plus 8/3, which is just 4.